Okay, so dear students, I hope everything is fine and you're able to, I mean, I'm audible. So let's start our session. So at first I'll be raising this thing, just hold on. Let me check if there is any technical issue. Okay, so now everything is fine. I hope everything is visible properly here. Anybody's having any issue, please keep a comment in the chat box. Your comments are really appreciated. Okay. Okay. And now let me check. We were in the previous session. Okay. And now let me check. We were in the previous session. Till now we have studied gravitational potential energy. Okay. So now we'll see gravitational potential energy of an object due to Earth. So it's very easy. Okay. Suppose you are having the Earth's surface. This is your Earth's surface. Okay. So this is the Earth of mass m, and radius of the Earth is r. This is the radius of the Earth. Okay. So now suppose if you are holding an object above the Earth's surface. So somewhat if I say that something and suppose at random r distance. Here you are holding some m naught mass. Okay. So now the question arises, if you want to write the potential energy of this system, what will be the answer? Please write it down. See now how to solve it. We know this thing. This Earth is like a solid sphere, and the solid sphere is having a mass capital M. Okay. For the solid sphere cases, we already have assumed this, that for the solid sphere cases, for the distance which is greater than the radius, we were having the gravitational potential energy, or the gravitational potential, if we say, as constant. So here also, I'll be writing for potential energy, or basically the interaction energy of the system. When I say the interaction energy of the system, I basically mean this. The interaction energy of this m naught mass and interaction energy of this capital M mass. Such that point to point difference, I mean this m naught and the center of the solid sphere is smaller distance far apart. I hope you're able to understand the things. We know this thing. The gravitational potential was also having the minus sign. So here, for the potential energy, the sign will also come negative. Please note it down. Now in this series, the next article, which is very important, is to understand how the gravitational potential energy changes. Or it's not required to understand, and this you can remember the expression. It's very important for the applications of the questions. So we'll see that how the gravitational potential energy changes when the object is lifted up from the Earth's surface to height h. Okay, let's understand it. So now we'll understand basically the change in potential energy, gravitational potential energy of the Earth. Okay. So you will write, we already have seen in work energy power chapter that if you are lifting this block or this duster at a height h from the Earth's surface, so at the Earth's surface, you will assume the gravitational potential energy as zero, and at height h, you will assume the gravitational potential energy as mass of the block or duster, acceleration due to gravity into height, mgh. Here, for these cases, when h is very, very less than r, but comparable to r, we know that the Earth's surface or the Earth is having the radius equals to 6,400 kilometers. So if it's very, very less, but comparable kind of, so then we'll say the potential energy changes in such a manner as per written. This expression which you will be seeing on the board is extremely important. So please always remember that. I hope you're able to understand the things. Now, based on this, we'll be solving a very interesting numerical. The numerical here is on the screen. Please solve this question. Remember, the hint for solving this question is the same which is just taught to us. Was that? That is the change in potential energy is basically mg h, that is the height from the Earth's surface, upon 1 plus h by r. Apply this and you will get the answer. You have 2 minutes for this. Okay, so the time is up now. I hope you're able to solve it. Students, this is a very interesting and an easiest question. What's the reason behind this? You just keep and try to understand this. That expression which we have just studied just recently, what was that? I hope you remember this. So now it's saying the work done to raise a block of mass m from surface of Earth to a height which is equals to the radius of the Earth. Just apply it. Height is equals to radius of the Earth. So whatever is the change in the potential energy which just came out here, that is equals to mg r by 2. This is in turn equals to external work done or the work done. Okay. So we'll say this contributes to work done. This is a required answer. Please note it down. Okay. So now we'll erase this. Now the next topic which we're going to study is basically escape velocity. First of all, let's understand what is this escape velocity is. So suppose you are like a Superman and you are throwing, suppose I'm throwing this. Okay. So I hope you have seen the movie Shaolin Shocker. And that what happens, the person, I mean, he kicks the football and the football never comes back, a kind of thing, although it was in some other area. So, I mean, you just give such a velocity to a mass m naught that it escapes the gravitational field intensity or the object m naught, which is just projected with some velocity v naught, it escapes the gravitational field influence of the Earth's surface, or the effect of the Earth's surface, is that velocity is basically known as escape velocity. Let's derive it. Now we'll see that this m naught is at the Earth's surface. When this m naught is at the Earth's surface, it means its potential energy is equal to, and on the Earth's surface, it's been provided a velocity which we will find it out as escape velocity. Okay. Now, as per the definition of the escape velocity, we know this thing, that the velocity v naught provided to the particle such that it escapes the gravitational field influence of the Earth. So when the particle escapes the gravitational field influence of the Earth, we can treat it to be the location, the final location of the particle, like, or the position. It's not finite, it's not definite, it's infinite. So now by applying the energy conservation theorem, we can find the escape velocity. So when you will solve this, you'll find that this escape velocity comes up to be square root 2 g, which is universal gravitational constant, into mass of the Earth upon radius of the Earth. So the escape velocity, which is being provided to the particle of mass m naught, in its mathematical formula, there is no m naught being written or included. So that's a very interesting thing. Remember, the escape velocity is twice under root twice of gm by r. Okay. So there is one more format of this. First, please note it down. I hope you have noted it down. We have just derived the formula for we have just derived the formula for escape velocity. Now we'll see a little bit manipulation in that. Okay. We know the formula for acceleration due to gravity in terms of capital G, M, and radius of the Earth. So in terms of acceleration due to gravity, escape velocity is written as root 2 or under root or square root 2gr. When I say g, it means small g, which basically means acceleration due to gravity. Okay, please note it down. Now, if we apply the values, and if you wanted to find the numerical value, what's the answer is, let's check. Values which I'm using for G and R are basically approximated values. So you will say if you are projecting any particle with 11.2 kilometer per second, it will never come back. Never come back means what? Never come back on the Earth's surface. Never. Never. It will take the trajectory. Yeah, if we go into the depths, that what kind of trajectory it will be? It can be circular motion. It can be circular motion. It will never be circular motion, by the way, because it will, if it's a circular motion, it will take the form of orbital velocity. So it can be kind of hyperbolic, or it can be linear, it may be linear. But this is beyond our scope. We'll not determine those things. Please note it down. After this, we'll see orbital velocity. I hope you have noted it down. Okay. Now I'll understand orbital velocity. What's the difference between escape velocity and orbital velocity? Escape, you already know that the object will never come back. I mean, it's went away under root 2 gm by r or under root 2 gr, 11.2 kilometer per second. But for orbital, we basically say it's like a satellite velocity. I mean, suppose if it's like, you have, suppose you have watched some kind of cartoons like Doraemon and all those things. We have the technology, futuristic technology. Even if we see the practical things, we have the satellites. So satellites basically orbit around the planet. So if we say our satellite, any of the satellites, say PSLV or anyone, so they are basically orbiting the Earth surface. They're orbiting around the Earth surface. When a satellite orbits around the Earth's surface, it's required to follow certain guidelines, a strict velocity. So the strict velocity is basically known as orbital velocity. If you are giving a particular object a velocity which is equals to orbital velocity, so it will be orbiting around the Earth's surface. I mean basically orbiting around very far away, but it will orbit the Earth from all directions, like a circular motion basically. If you treat the Earth to be elliptical or oval, so it will be like oval motion or elliptical motion. Okay. But basically we treat it to be like a circular motion for the ideal cases. Let's derive it. So we know this thing. If we draw the FBD of this satellite, the satellite is performing circular motion or orbital motion. So for the orbital motion or the circular motion, we know a particle can only sustain the circular motion trajectory if it is having a centripetal force. If we see on the satellite, suppose this is the Earth, and this is a satellite. So it's orbiting in a circular motion. So what is happening? There will be a center seeking force, which will support play the role of centripetal force. Here it is basically the gravitational force or the universal or the Newton's universal law of gravitation, which is G m naught upon small r, because it's far away from the center of the Earth. Okay. So we'll say orbital velocity will be square root under root G, capital G, that is universal gravitational constant, mass of the Earth upon small r. Okay. So this is known as orbital velocity. So as we did for the escape velocity, we'll also perform the same action for the orbital velocity. So ideally, what we do for the derivation, we take a good, see, practically we know it's not like this. It is rotating just on the surface. Because we know if we go towards the core of the Earth, that point center of that lies there, practically. And it's not possible practically the Earth's surface, it's they are the layers of the layers, troposphere, stratosphere. So in space, I mean, it's a particular region the satellite orbits. So that's why we take smaller. But for now, for mathematical analysis or for the application purposes, we take smaller equals to the radius of the Earth. Okay. So, and when I take smaller equals to capital radius of the Earth, it means kind of from the center. So we get this expression. Now, for escape, it was under root 2gr, and for this, it's under root gr. So there is a root 2 factor multiplicative difference. So now we'll analyze that. Please note it down first. So now we'll understand this thing that comparison between escape and orbital velocity. Or if we say in terms of orbital, what's escape is. You always have to remember this expression. It's intensely important. Okay, very important, extremely important. Please note it down fast. Now we'll see time period of the revolution of the satellite around the Earth's surface. Okay. So we'll understand like this that if a satellite is orbiting around the Earth's surface, so if it's in the circular motion, because it's an orbital motion, so circular motion, it basically covers a periphery that is, or the circumference of the circle that is 2 pi r. Okay. Because the satellite is moving with the orbital velocity. So I'll put in the denominator of this time period formula, orbital velocity. And we know that orbital velocity is basically in the acceleration due to gravity format, it is under root gr. Okay, we know this under root gr. So let's take from the basic format. We know this was the basic format of the formula. Okay. Now we'll do the same assumptions again and again. So now we're going to do some manipulation here. Let's check. First of all, please note it down up to this. This is square term. Here, capital R radius is in the square term, so that will come out of the square root. So this is our final expression. So we'll say, or we'll make a conclusion from this, that time period of revolution of the satellite is directly proportional to what? Basically, it's square root. Okay. So you can say like this, that square of the time period of revolution of the satellite around the Earth's surface is directly proportional to the radial distance q. Okay. So when we will be studying Kepler's three laws, or the three laws of Kepler planetary motions, at that time you'll be able to understand that this also comes among one of the laws. Okay. Please note it down. Now we'll do a little bit modification in this. Suppose the particle is at the Earth's surface or on the Earth's surface. I mean, particle is on the Earth's surface. So small r will be equivalent or equal to, basically, small r will be equal to the radius of the Earth. Let's do manipulation. So for this, the formula is time period is equal to 2 pi under root capital R by G. This is for the Earth's surface. So please note it down, and then we're going to end the session. In the next session, we'll understand the energy of the satellite, and finally we'll end the gravitation series. Thank you so much.